Okay, hello Cloud Gurus, and welcome to this lecture where we're going to dig into data flows. Now, depending on your background, this may all be very natural for you, or this may seem like a completely new concept. And for most of you, it'll probably be somewhere in between. But no matter where you're at right now, I hope this lecture will help you to apply this way of thinking to all sorts of situations that you come across. Okay, so let's get started. The first thing I want to say is that data flows are everything. Well, in information technology, anyway. I mean, IT is literally all about applying technology in useful ways to handle information. Because of this, I've seen a very strong correlation between data flow thinking and success in this field. In fact, I would even go so far as to say that if you learn to identify and control data flows, then you will succeed. But if you just try to memorize situations and how to respond to them, then you won't. Now, in the context of this course, I definitely want you to be able to pass the exam, but I want you to do that because you'll actually be successful in the real world, not just because you learned how to parrot back the right answer for some questions. So I think this applies to both real world and exam situations. Okay then, so what is a data flow? Fundamentally, it's about taking some data or information and moving it around, processing it in interesting ways, and remembering it. So we'll often associate these three things with three classes of services, being network services, compute services, and storage services. And while that's a good rule of thumb, it's important to not box our thinking in as rigidly as that. For example, moving data could also include loading stuff from disk into memory, or linking up services through some integrations that aren't specifically networking. And processing also includes how a database system might respond to a query, or setting a messaging service up to filter what passes through it. Remembering also includes things like caching data in RAM or a content distribution network. So do remember the categories on the left, but the stuff on the right is the right way to think about data flows. Alright, so to help us think about data flows, we need to use mental models. A mental model is a simplified representation of reality, which is used by your mind to anticipate events or draw conclusions. It's what your brain builds when you understand something, or the way that your brain organizes information it learns into hierarchies. Now, beyond just one mental model, though, it's also important to recognize that systems do combine. You build larger systems out of smaller ones. And to do that effectively, we need to use abstractions. A lot of the time, it's not that important what the details are of what's happening inside of a subsystem, but it's usually very helpful to understand at least the basics of what's going on. And so being able to zoom into subsystems and back out into the bigger system is a valuable skill. But I'm not going to rehash all of that. Let's move on to a practical example of a data flow. Now I'm going to skip or gloss over a lot of things here because I care more about the core data flow and not so much about the internal details of every action or each subsystem. But we're going to try and break down the data flow of both control information and other data like web pages and whatnot that happened in the Cloud Shell lab that you just went through. Let's start with your machine. On your machine, you run a web browser. I'm sure you've got other things running on that machine too, but those things don't really affect this data flow. Now in this web browser, you open up the GCP console, and that reaches out to the Google Cloud control plane. Now of course, this isn't an airplane type plane, it's like a mathematical plane, a surface where you can control everything that happens in GCP. Now when we open up Cloud Shell, Google Cloud makes sure that we have some persistent storage available and finds a machine to host our Cloud Shell instance. On this machine, it starts a container, and in that container, it starts a secure shell server. Now, there might also be some other things running on that machine, like maybe more Cloud Shell containers for other clients, but it doesn't really matter to us. What matters to us is that we can now connect to this Cloud Shell from our browser. Now in this, we run a git command that connects to GitHub to get the lab files, and it stores those files on the Cloud Shell persistent storage. When that's finished, we run node against those files. Node will load them up, and then sit there waiting for a request that comes in on port 8080. Now in your web browser, you try to connect to port 8080, But localhost is just pointing back to your machine, so that doesn't work. Instead, we use the web preview, where the Google Cloud sets up a proxy for us. Now when we connect to the URL for that particular proxy, it connects through to Node running on port 8080 on the container on the Cloud Shell host machine. So when we see the response, we see what we expected. Then we open up the Cloud Shell editor, which connects to the lab files, and then we make a change. We save those changes back to the persistent storage, and then reload our browser, which connects back through the proxy and onto port 8080 on the Cloud Shell container. Now here's something that really shows off the power of data flow thinking. When you look at it this way, it's really obvious what response we're going to get back to that page running in our web browser. There has been no data flow between the lab files and the node process. So when we talk to the node process, we're definitely going to get the old version of the page. If we want to see those updates take effect, we have to get that data into the node process somehow. So that's why we stop the node process and then restart it using nodemon. So again, when the node process starts, it reaches out and grabs the files, the updated ones in this case. And the nodemon process puts a watch on those files. So now when we change the files again in the editor and save them, nodemon notices that they've been changed and restarts the node process. And of course, when the node process starts, it reaches out and grabs the files. This is how the data is flowing through this system. But those new updates have still only made it to the node process themselves, so we need to reload the browser and have it connect back out again. Of course, this time we see that it will get the updated response because the data has flowed to that node process before this request comes in. Now the next thing we do is to tear down the nodemon process and the node process it's controlling, and then run nodemon again, but this time against a file that's on port 8081. Of course, nodemon puts its watch on the files, and the node process loads them from persistent storage. Now when we reload the page that we were using to look at port 8080, it connects through the same proxy, but that proxy doesn't find anything on port 8080 anymore. That process is gone. Since we have no more use for that 8080 page, we close it down, and eventually Google Cloud will get around to cleaning up that proxy as well. Since we want to see what's running on port 8081, we change the port, have Google Cloud create us another proxy, open up that web page, and connect through there. Since that proxy is configured for port 8081, it does find the new node process and gets the response. Well, literally 138 slide animation steps later, we got through the whole data flow. Now, if you look at this closely, you'll see lots of places where there's data movement, data processing, and data storage. There's definitely some long-term storage here, but there's also a lot of short-term storage too. And there's definitely processing as well. I mean, the response to the different web pages is definitely not the same as the source code, the lab files directly. Those code files were interpreted by the node process so that it knew how to respond. Okay, so do you feel like this was helpful? Do you think that you could apply this process of thinking to other systems? Now, if you don't feel like you followed every step in this, that's okay too. But I would then recommend that you rewatch this lecture and redo the lab so it will make sense to you. And please do ask for help on the forums if you get stuck. But now let's take a look at this understanding and use it to make some predictions. So for example, what happens if I update the lab files that are stored in GitHub? How would you update your lab files? And what if we both changed the same lab file? And how about if you wanted to get the lab files back to the way they were before you changed them? Do you know some ways you could do that? I can immediately think of 3 possibilities. Now what happens if the Cloud Shell persistent storage becomes temporarily unavailable? When and how might you notice that? Would it be when you refresh the browser? Why or why not? What happens when Cloud Shell times out and it tears down your Cloud Shell container? What would you lose then? And how would you get things back to the way they were at the end of this lab? Understanding this mental model and its data flows is very strong. You'll need to do this same sort of thing with other GCP services too. Things like how Kubernetes is structured with nodes and pods and deployments and services, or how source code makes its way from a developer's machine and eventually becomes something useful to the end user on their machine, working its way through continuous integration and continuous deployment systems and stuff like that. Now let's apply this data flow way of thinking to a new scenario. So let's imagine this situation. You're at a dance recital, and the ballet class teacher was going to take this group of girls out for treats after their performance. But an emergency has come up, and she's now asked you to take these kids home. You want to choose an efficient vehicle, and you consider your options. Your first option is this plane. Now, this is not really the right vehicle for this job. Of course, you know that intuitively, but let's think about the details as an exercise. So, not only are plane tickets rather expensive, but the data flow here just doesn't work. And I don't just mean the flow to get plane tickets for all of them. Okay, so given the scenario I posed, you might expect the flow to be something like this. The dancers are on stage, then they go off stage, they get in the vehicle, you go to the first home, the second home, the third, fourth, fifth, sixth home, and you're done. But trying to take these kids home using this airplane would mean a flow more like this. They start on stage, they go off stage, but then you have to get to the airport. I mean, I doubt the recital's at the airport, right? And even though you take the plane, you land at another airport. So how would you get everyone home from the airport at the destination? There are some critical missing pieces in this flow. That doesn't mean that this is absolutely wrong, but it's certainly incomplete, and you have to make some assumptions about what else is going on here. Okay, let's take a look at our next option. Here we have a very small car. Now you could probably say that this vehicle is fuel efficient, but I don't really think it's going to be efficient for this job. Think data flow. What is the practical process by which you get a whole bunch of kids home using this car? After they come off stage, I guess you can really only fit one kid in the car. So do you drive that person home and then come back to pick up the next kid? How long would this process take? And who would watch the remaining kids when you're driving each one home? This might be a workable process, but there are definitely some issues that you'd have to figure out. And in terms of efficiency, if all the homes were close to the theater, this might not be so bad. But if all the homes are close to each other but far away from the theater, then this becomes particularly bad. Let's look at our next option. Well, this vehicle has enough space to hold all the kids at the same time, but how would you use this vehicle? I mean, you can't mail the kids home. So are you going to borrow this truck from a mail person? But even still, mail trucks don't have passenger seats. They're for transporting cargo. So this vehicle will not enable you to safely and legally drive these kids home. The question didn't call this out, but safely and legally are always implied. Next. Okay, school buses can definitely be a safe and legal way to transport many children, but is that the case for you? Do you have a bus driver's license? Also, I didn't really say in the scenario how you would come by these vehicle options, but practically speaking, you usually have to plan some time ahead to have a bus and driver ready to transport kids. And in the scenario I described, you seem to only have the little time while they finish their dancing to get this all arranged. Again, the flow of getting everything worked out here seems to be a bit of an issue. Okay, now we're getting somewhere. This minivan is made to cart around a smaller group of people, especially kids. But does it have enough space? Well, I thought it looked like it, so let's come back to this one. Now this hodgepodge option seems like it might be interesting at first, and you start to think more closely about them, like maybe that VW bus, because you think maybe they'll work. But if you look closer, you'll see that these are actually just toys. What looks like it might be a reasonable option is actually not. Next. Okay, Now this is another interesting option. As a slightly larger vehicle than the minivan, this might be a bit less efficient on fuel, but really that's just a guess and that might be wrong. We don't really know for sure. But we do see a difference in what looks to be seating capacity. So let's take a closer look at the scenario again. All right, well, we could count the destination houses, 1, 2, 3, 4, 5, 6. But that's really getting confused if you think about it. It doesn't matter so much how many times we stop, it matters more how many seats we need. So let's count the kids instead. 1, 2, 3, 4, 5, 6, 7. Only 7 kids? Maybe go for the minivan then? But let's look more closely again. 1, 2, 3, 4, 5, 6, 7, 8, 9 kids plus a driver. When we were waving our hands at the numbers, these two options looked pretty similar. But when we looked more carefully at the flow and thought instead about how each individual person would need to sit in a specific seat, we saw that the minivan would require now 2 trips, and leaves open the question about who supervises the kids, whereas the bigger van can do the job in 1 trip and brings everyone along at once. So now the decision is pretty clear. Alright, let's look at what I hope you take away from these exercises. I hope you can see how data flows are the foundation of every system, and they're made up of moving, processing, and remembering information, not just network, compute, and storage components. When you're thinking about data flows, make sure you build mental models. These help you make predictions about what should or will happen. And identify and think through the data flows, because doing this can highlight a lot of potential issues. We also saw how the requirements and options that we're looking at are not always clear, and while the example I gave is a little bit silly, this is especially true in the real world. So the skills we practiced here are critical for both real-world and exam situations. Alright, a lot of you will probably still have some questions about all of this, and that's fine. I recommend that you try rewatching this video and redoing the lab a couple of times to see if it clicks for you. And of course, as always, you can also reach out and ask questions. Please do. In any case, when you're ready to move on, I'll see you in the next lecture. Thank you.